Today, we'll do a quick review of the essential mean value theorem questions. This question is to learn how to apply Lagrange mean value theorem and verification. Determine whether the function 4x cubed minus 5x squared plus x minus 2 satisfies the Lagrange mean value theorem on the interval from 0 to 1. Clearly state the conditions that must be checked and find the value or values of 11 between 0 and 1 that make the theorem hold true. First step is to check the theorem's conditions. To use the Lagrange mean value theorem, two things must be true. First, the function must be continuous on the closed interval from 0 to 1. Second, it must be differentiable on the open interval between 0 and 1. In this case, the function is a polynomial, specifically for x cubed minus 5x squared plus x minus 2, and all polynomials are continuous and differentiable everywhere. So, the conditions are fully satisfied. Next step is to apply the Lagrange mean value theorem. Now, the theorem tells us that there must be at least one point, which we'll call 11, somewhere strictly between 0 and 1, such that the derivative at 11 is equal to the average rate of change from 0 to 1. Let's calculate the average rate of change. When x is 1, the value of the function becomes 4 minus 5 plus 1 minus 2, which equals negative 2. When x is 0, the value is 0 minus 0 plus 0 minus 2, which is also negative 2. So, the average rate of change is 0. That means we're looking for a point 11 between 0 and 1 such that the derivative of the function at that point is 0. Next step is to find where the derivative equals the average rate. Now let's compute the derivative of the function. The derivative of 4x cubed is 12x squared. The derivative of negative 5x squared is negative 10x. The derivative of x is 1, and the constant term disappears. So, the derivative is 12x squared minus 10x plus 1. We set this expression equal to 0 and solve for x. This is a quadratic equation. 12x squared minus 10x plus 1 equals 0. Using the quadratic formula, we get the solutions as open parenthesis 5 plus or minus the square root of 13 close parenthesis divided by 12. We now check whether both roots are between 0 and 1. The square root of 13 is approximately 3.6. So the two values are approximately 0.11 and 0.71. Since both are strictly between 0 and 1, they satisfy the theorem. Therefore, the function does satisfy the Lagrange mean value theorem on the interval from 0 to 1. And the value or values of 11 that make the derivative equal to the average rate of change are open parenthesis 5 plus or minus the square root of 13 close parenthesis over 12, which both lie between 0 and 1. Always begin by checking continuity and differentiability. It's the easiest place to forget and the most common reason students lose marks on mean value theorem problems. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This question is to determine the number of its inflection points of a symmetric function. Consider the function y equals the square of the quantity x minus 1 times the square of the quantity x minus 3 star. How many inflection points does the graph of this function have? Options. First step is the symmetry insight. This function is symmetric with respect to the vertical line x equals 2. That means if there's any inflection point on the left of x equals 2, there must be another on the right. So the total number of inflection points has to be either 0 or 2, never 1 or 3. A common mistake is assuming symmetry guarantees just one inflection point at the center, but that's not true for this kind of curve. Next step is to first derivative analysis. Now we differentiate the function. The first derivative turns out to be a product of three terms. X minus 1 times x minus 2 times x minus 3, all multiplied by 4. This derivative tells us about the slope of the curve, but to find inflection points, we need to examine where the concavity changes. That means we need the second derivative. Next step is to using Rawls' theorem on the derivative. Let's look at the first derivative. It has three real roots, at x equals 1, x equals 2, and x equals 3. According to Rawls' theorem, if a smooth function has equal values at the ends of an interval, then its derivative must be 0 somewhere in between. Applied here, this guarantees that the second derivative has at least two real roots, one between 1 and 2, and another between 2 and 3. That means the original curve changes concavity at two distinct x values. In other words, it has two inflection points. When the first derivative is a cubic with three distinct roots, the second derivative will usually have two real roots. That's your clue for spotting two inflection points, especially when the function is symmetric. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This question is to use the mean value theorem. Let the function g of x be equal to x plus 1 divided by x plus 3. Part A. Show that the function g of x satisfies the conditions required by the mean value theorem on the interval from 2 to 6. Part B. Then, find all values of c between 2 and 6 that satisfy the conclusion of the mean value theorem. First, verifying conditions of the mean value theorem. We start by checking if the function g of x equals x plus 1 divided by x plus 3 is continuous on the closed interval from 2 to 6 and differentiable on the open interval from 2 to 6. Since this is a rational function and the denominator, which is x plus 3, never becomes 0 within our interval, the function is continuous and differentiable on the required intervals. So, the mean value theorem applies. Next step is to compute the average rate of change. We now compute the average rate of change of g over the interval from 2 to 6. This means we take g of 6 minus g of 2 and divide the result by 6 minus 2. Let's evaluate the function at both endpoints. G of 6 is equal to 6 plus 1 divided by 6 plus 3, which is 7 over 9. G of 2 is equal to 2 plus 1 divided by 2 plus 3, which is 3 over 5, which simplifies to 2 over 45. Next step is to find the derivative of the function. Next, we take the derivative of g of x, using the quotient rule. The numerator of g is x plus 1, and the denominator is x plus 3. Using the quotient rule, we get the derivative of the numerator, which is 1, times the denominator, which is x plus 3, minus the numerator, which is x plus 1, times the derivative of the denominator, which is also 1. So, in the numerator we have x plus 3 minus x minus 1, which simplifies to 2. In the denominator, we have x plus 3 squared. So the derivative, which we'll call g prime of x, is equal to 2 divided by the square of x plus 3. Next step is to set derivative equal to the average rate of change. According to the mean value theorem, there exists some c between 2 and 6 where the instantaneous rate of change equals the average rate of change. So we set 2 divided by the square of c plus 3 equal to 2 over 45. Canceling the 2 on both sides, we get that the square of c plus 3 is equal to 45. Taking the square root of both sides, we get c plus 3 equals the square root of 45, which is 3 times the square root of 5. Then, subtracting 3 from both sides, we find that c equals 3 times the square root of 5 minus 3. To check that this value lies between 2 and 6, the square root of 5 is a little over 2.2, so 3 times the square root of 5 is about 6.7, and subtracting 3 gives about 3.7, which lies in the open interval from 2 to 6. So this value is valid. The value of c that satisfies the conclusion of the mean value theorem is 3 times the square root of 5 minus 3. When solving problems like this using the mean value theorem, especially with rational functions, focus on simplifying the derivative and equating it to the average rate of change. Watch for squares in the denominator and remember to check whether your final c is actually within the interval. That's it for this question. This question is to find the derivatives of even functions. Suppose a function f of x is differentiable for all real numbers and satisfies the condition that f of negative x equals f of x for every x. If you're told that the derivative of f at negative x naught is equal to negative k, where k is not equal to 0, then what is the value of the derivative of f at positive x naught? First step is to recognize the type of function. We are told that f of negative x equals f of x. This means that f is an even function. The key fact to remember is, if a function is even, then its derivative is an odd function. That is, the derivative at negative x is equal to the negative of the derivative at positive x. Next step is to apply the identity for the derivative. Now, we are given that the derivative of f at negative x naught equals negative k. Using the property that the derivative of an even function is odd, we can say the derivative at negative x naught is equal to the negative of the derivative at positive x naught. So, negative k equals negative of the derivative at x naught. This means the derivative at x naught must be k. The final answer is, the correct choice is A. Students often mistakenly assume that the derivative of an even function is also even, but that's incorrect. Just remember, if the function is even, its derivative is odd. That's the key. When the function is even, its derivative will always be odd. That means, to find the derivative at a positive x, just take the negative of the derivative at the negative x. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on the notification bell. Press the like button. Thank you so much. This problem is typically at the level of a calculus assignment or quiz. If you're preparing for final exam level calculus questions, feel free to check out my YouTube videos linked above. This question is about Cauchy mean value theorem application and solutions. Let the function g of x be the natural logarithm of 1 plus x, and let the function h of x be x squared. consider the closed interval from 0 to 1. Please verify that both functions satisfy the conditions of the Cauchy mean value theorem on this interval. Then, find a value c between 0 and 1 such that the difference in values of g at 1 and 0 divided by the difference in values of h at 1 and 0 is equal to the value of the derivative of g at c divided by the value of the derivative of h at c. Let me check the conditions of the Cauchy mean value theorem. First, the function g of x, which is the natural logarithm of 1 plus x, is continuous on the closed interval from 0 to 1. It is also differentiable on the open interval between 0 and 1. Second, the function h of x, which is x squared, is also continuous on the closed interval from 0 to 1 and differentiable on the open interval. Its derivative, h prime of x, is equal to 2 times x, which is never 0 within the open interval from 0 to 1. So, all the conditions of the theorem are satisfied. Next step. By the Cauchy mean value theorem, there exists some value c between 0 and 1 such that the difference g of 1 minus g of 0 divided by h of 1 minus h of 0 is equal to the value of g prime at c divided by h prime at c. Next step. Now let's compute the left-hand side, that is, the constant ratio. The value of g at 1 is the natural logarithm of 2. The value of g at 0 is the natural logarithm of 1, which is 0. The value of h at 1 is 1 squared, which is 1. The value of h at 0 is 0 squared, which is 0. So the entire ratio becomes natural logarithm of 2 divided by 1, which is simply natural logarithm of 2. Next step. Next, compute the derivatives. The derivative of g, which is g prime of x, is 1 divided by 1 plus x. The derivative of h, which is h prime of x, is 2 times x. Therefore, the ratio of the derivatives is 1 over the product of 2 times x and 1 plus x. We set that equal to natural logarithm of 2 and solve for x. Next step. Multiply both sides of the equation by 2 times x times 1 plus x, and you get 1 is equal to 2 times x times 1 plus x, all multiplied by the natural logarithm of 2. 2 times x squared plus 2 times x minus the reciprocal of natural logarithm of 2 equals 0. Apply the quadratic formula to solve for x. This gives x equals negative 2 plus or minus the square root of 4 plus 8 divided by natural logarithm of 2, all divided by 4. Take the positive root only, since c must be in the open interval from 0 to 1. So this gives the required value of c that satisfies the theorem. This problem is a general introduction to the Cauchy mean value theorem. The first thing to always do is check the assumptions. Make sure both functions are continuous on the closed interval and differentiable on the open interval. Also confirm that the derivative of the second function, the one in the denominator, is not 0 anywhere in that interval. Next, compute the average rate of change, that is, the difference in function values divided by the difference in the second function's values. Then, equate that to the ratio of the derivatives and solve for x. This part is usually where the algebra kicks in, but don't worry. The trick is to stay calm, follow the steps, and apply the quadratic formula if needed. Choosing simpler functions like the logarithm of 1 plus x and x squared helps students build intuition and confidence before tackling trickier functions. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams. The question is to determine which of the given intervals is guaranteed to contain a root of the function by the intermediate value theorem. This problem is typically at the level of a calculus assignment or quiz. If you're preparing for final exam level calculus questions, feel free to check out my YouTube videos linked above. 2 raised to the x plus x squared minus 10 equals 20. Only use the values of the function at the endpoints of each interval to justify your answer using the intermediate value theorem. Let's define the function f of x as 2 raised to the x plus x squared minus 10. We are asked to find which interval must contain a solution to the equation f of x equals 20. First step is to check continuity. The function consists of an exponential part and a polynomial part, both of which are continuous for all real numbers. So we know that the intermediate value theorem can be applied. Next step is to evaluate the function at the endpoints of the interval from 2 to 3. First, evaluate f of 2. 2 raised to the power of 2 is 4. 2 squared is also 4. So 4 plus 4 minus 10 equals negative 2. Then, evaluate f of 3. 2 raised to the power of 3 is 8. 3 squared is 9. So 8 plus 9 minus 10 equals 7. Now we observe. Negative 2 is less than 20. 7 is also less than 20. So 20 is not between the values at the endpoints. Therefore, this interval does not contain a solution. Next step is to check the interval from 4 to 5. Evaluate f of 4. 2 raised to the power of 4 is 16. 4 squared is 16. So 16 plus 16 minus 10 equals 22. Now f of 5. 2 raised to the power of 5 is 32. 5 squared is 25. So 32 plus 25 minus 10 equals 47. Here, both endpoint values are greater than 20. So again, 20 is not between the values. This interval does not contain a solution either. Next step is to check the interval from 3 to 4. We already know f of 3 is 7, and f of 4 is 22. Now, 7 is less than 20. 22 is greater than 20. So the function changes from below 20 to above 20 between x equals 3 and x equals 4. By the intermediate value theorem, there must be at least one number between 3 and 4 where the function equals 20. The correct answer is option D, the interval from 3 to 4. When working with the intermediate value theorem, remember these key ideas. First, you must check that the function is continuous over the interval, and most common functions like polynomials and exponentials are. Second, you only need to plug in the two endpoints of each interval and check the function values of those points. Third, look at whether the value you're solving for lies between the function's values at the endpoints. If it does, then the theorem guarantees there's at least one solution inside the interval. You don't need to actually solve the equation. You're only showing that a solution must exist in that range. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams. This new question is to determine if a differentiable function with equal endpoint values on an interval must have a point within that interval where its derivative is 0. Suppose a function f is differentiable on the interval from -1 to 1, and it is given that the value of f at -1 equals the value of f at 1. Does there necessarily exist a number c, such that c lies strictly between -1 and 1, and the derivative of f at c equals 0? Justify your answer. First step is to recognize the theorem to use. Since the function f is differentiable on the interval from -1 to 1, it is also continuous on that same interval. That allows us to use the mean value theorem. This theorem tells us that if a function is continuous on a closed interval and differentiable on the open interval, then there must be at least one point where the instantaneous rate of change equals the average rate of change over the interval. Next step is to apply the mean value theorem. According to the theorem, there must be some number c between -1 and 1, such that the derivative of f at c equals the average change in the function over the interval. In this case, that average change is the value of f at 1 minus the value of f at -1, all divided by 2. Next step is to use the given condition. We are told that the value of f at -1 equals the value of f at 1. So when we subtract them, the result is 0. Dividing 0 by 2 still gives 0. So the derivative of f at the point c is 0. Next step is to interpret the result. This means there is indeed a number c between -1 and 1, where the derivative of f is 0. So the statement is true. A common mistake is to confuse this situation with other theorems. Here, since the function has equal values at the endpoints, this is actually a perfect example of Rawls' theorem, which is a special case of the mean value theorem. Whenever a function is smooth and has the same value at the start and end of an interval, you can be sure that somewhere in the middle, its slope must be exactly 0. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel MathTutor8285 and turn on the notification bell. Press the like button. Thank you so much. This new question is to determine if the mean value theorem applies to a given function over a specific interval. Determine whether the mean value theorem applies to the function y equals 5 plus the absolute value of x on the interval from -1 to +1. Justify your answer. First step is to recall the conditions for the mean value theorem. For a function to satisfy the mean value theorem on a closed interval from a to b, it must meet two conditions. First, the function must be continuous on the closed interval, including the endpoints. Second, it must be differentiable on the open interval, which excludes the endpoints. Next step is to check continuity on the interval from -1 to +1. The function y equals 5 plus the absolute value of x is continuous everywhere, including this interval, because absolute value functions do not have any breaks, jumps, or holes. So continuity is satisfied. Next step is to check differentiability on the open interval from -1 to +1. To evaluate this, consider how the function behaves. If x is greater than 0, then the absolute value of x equals x, so y equals 5 plus x. If x is less than 0, then the absolute value of x equals -x, so y equals 5 minus x. At x equals 0, the function simply evaluates to 5. Now, look at the derivative. When x is greater than 0, the slope is 1. When x is less than 0, the slope is negative 1. But at x equals 0, the left-hand and right-hand derivatives do not match. The slope coming from the left is negative 1, and the slope coming from the right is positive 1. Because these two do not agree, the function is not differentiable at x equals 0. And since 0 lies inside the open interval, the differentiability condition is not satisfied. Next step is the conclusion. The function is not differentiable on the entire open interval from -1 to 1, so the mean value theorem does not apply to this function over this interval. When checking for the mean value theorem, don't stop at continuity. Always check whether the function is smooth and has a well-defined slope everywhere in the open interval. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on the notification bell. Press the like button. Thank you so much. This question is to solve for a single positive real root. Let f of x be defined as x raised to the 5th power plus x minus 1. Prove that this equation has exactly one positive real solution. First step, show that there is at least one positive root using continuity and the intermediate value theorem. We begin by noting that f of x is a polynomial function, so it is continuous for all values of x. Let's evaluate the function at 2 points, when x is 0 and when x is 1. At x equals 0, f of x is 0 raised to the 5th power plus 0 minus 1, which equals negative 1. At x equals 1, f of x is 1 raised to the 5th power plus 1 minus 1, which equals 1. So, at 0 the value is negative, and at 1 the value is positive. Since the function is continuous between 0 and 1, by the intermediate value theorem, there must exist some number between 0 and 1. Let's call it 11, where the function equals 0. That confirms that there is at least one positive solution. Next step, prove that this positive solution is the only one using Rawls' theorem and the derivative. Now, suppose for contradiction that there are two different positive solutions. Let's call them a and b, where a is greater than b. That means f of a and f of b are both 0. The function is continuous on the interval from b to a and differentiable between them. By Rawls' theorem, there must be some point between b and, let's call it 11, where the derivative of the function is equal to 0. But let's compute the derivative. The derivative of f of x is 5 times x raised to the 4th power plus 1. For all positive x, this expression is always greater than 0, because both terms are positive. That means the derivative can never be 0 on any interval of positive x values. This contradicts our earlier assumption. Therefore, the original equation can have only one positive real root. Students sometimes forget that if the derivative is always positive, the function keeps increasing, which means it cannot turn around and hit the x-axis twice. If you want to prove a root is unique, check if the function is always increasing or always decreasing. That usually seals the deal. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This question is to learn how to apply bounding logarithms with a mean value theorem. First step is to understand the function we're dealing with. We are looking at the natural logarithm function, which we can call ln of x. This function is continuous for all positive values of x, and it can be differentiated as well. Since we're considering the interval from b to a, and we're told that is greater than b and both are greater than 0, the conditions are met for applying the mean value theorem. Next step is to apply the mean value theorem. By the mean value theorem, there must exist some number, let's call it 11, lying strictly between b and a, such that the difference between ln of a and ln of b is equal to the derivative of ln evaluated at 11, multiplied by the difference of minus b. Since the derivative of ln of x is 1 divided by x, this means that ln of minus ln of b is equal to 1 over 11, times the quantity of minus b. Next step is to use the fact that 11 lies between b and a. Because 11 lies between b and a, and since b is less than 11 and 11 is less than a, the reciprocal of 11 must lie between the reciprocal of a and the reciprocal of b. Now if we multiply everything by a minus b, which is a positive number, the inequality still holds. So, we find that the product of a minus b and 1 over a is less than the product of a minus b and 1 over 11, which in turn is less than the product of a minus b and 1 over b. But remember, that middle expression is exactly what ln of a minus ln of b equals. So this shows us that the product of a minus b and 1 over a is less than ln of a over b, and this is less than the product of a minus b and 1 over b. When you're asked to bound a logarithmic expression, try applying the mean value theorem to the natural log function. Just remember, it's all about finding the slope between 2 points and comparing it to the slope and in-between point. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much.